we were talking about black bodies and whether or not the Earth, with an atmosphere and with no greenhouse gases, could be a black body. And just to review, a black body is an object that emits everything that it absorbs. And it absorbs everything that comes at it. So that a black body will take in everything and emit everything. And if you think about that, we are looking at an atmosphere that does not have greenhouse gas, and we can think about it in terms of the sun emitting 100 units of light to us. Well, 30 of those units are going to be reflected right off the bat by the top of the atmosphere, and that's right here. And then the other 70 are going to pass through the atmosphere and be absorbed by the surface of the Earth. To be a black body, those 70 units have to be emitted right back out again. And the Earth is then taking in everything it can. The Earth's surface is taking in everything that it can, and it is emitting everything that it can in an atmosphere that does not have greenhouse gases. The Earth would be a black body, but we wouldn't be living there because everything would be ice, and we can't have sustainable life with ice everywhere. We live on this Earth because we have 3 phases of water. So in terms of that, let's look at the difference between being a black body and being a body in a state of radiative equilibrium. A black body absorbs everything that comes at it and emits everything that comes at it. A state of radiative equilibrium says that all systems, following the second law of thermodynamics, tend to a state of radiative equilibrium. If you've got incoming hot solar radiation, you will tend to want to cool that area. So hot and cold meet in the middle. To do that, we look at absorption and emissions evening out. That means that when absorption and emissions are evened out, there's no increase in temperature. When absorption is greater than emission, there is an increase in temperature. When emission is greater than absorption, there's a decrease in temperature. A state of radiative equilibrium, where the temperature stays stable in the system, is not the same as being a black body. A black body is taking everything in and emitting everything. A state of radiative equilibrium looks to balance temperatures and emissions in and emissions out, but they may not, absorption in and emissions out, but it may not be maximum absorption in and it may not be maximum emission out. Let's go into that a little bit more clearly. Let me get over here. There it is. The second law of thermodynamics says that every state tends toward an equilibrium. For instance, if you put ice in a soda, the ice is going to melt because it's going to balance the warmth of the soda with the cold of the ice, okay? If that's the second law, just a reminder, the first law is that energy cannot be created or destroyed, just transferred. Just a reminder for you. To get back to our atmosphere and reality. The reality is that our Earth's atmosphere does have greenhouse gases. So is our atmosphere a black body? And is our atmosphere making our system into a system of radiative equilibrium? 2 really good questions. The atmosphere around us that does exist with greenhouse gases that absorb very selectively means that our atmosphere is not a perfect absorber. And if it's not a perfect absorber, if it doesn't absorb everything that comes at it, then it's not a black body. The Earth's surface is a black body. The Earth's atmosphere is not a black body. The Earth will absorb everything that comes at it through the atmosphere, but the atmosphere is not letting everything come at it. Let's go in and explain that a little bit better. We can say the same thing we said before, that there are 100 units coming from the sun. And we can say the same thing that we said before, that the atmosphere at the top of the atmosphere will reflect off a total of 30 units, leaving 70 units to come down below the atmospherics, into the lower atmosphere, leaving 70 units in there. Of the 70 units that are in there, 19 units are going to be absorbed by the rest of the lower atmosphere and the clouds. That means 51 units are going to be allowed to get to the Earth's surface. So 51 plus 19, that's the same 70 we were talking about before when we didn't have greenhouse gases. So we're at the same place right now. Let's see how that changes a bit with the greenhouse gases on the way out. Okay? On the way out is the big difference with greenhouse gases. So that when it's inbound to Earth, we tend to find that there are 30 units kicked out right from the top of the atmosphere. It has nothing to do with greenhouse gases. They're just kicked out by reflecting off of the top of the atmosphere. When you do have greenhouse gases, there's another 19 units that are absorbed. What do they absorb? Well, what is the sun really putting out? The sun is really putting out ultraviolet energy, high energy waves, and it's putting out visible light. That's what's absorbed by those 19 units. Those greenhouse gases can absorb those units, and they prevent them from hitting the surface of the Earth. What you see here is that the Earth is absorbing nearly 100% of the UV. Guess what? That's the ozone in the stratosphere, and that's considered the lower atmosphere. And then you're absorbing quite a bit of IR in here as well. And that IR that's being absorbed in the clouds is actually IR that's being absorbed from CO2 and from water vapor as well. So that's what's being absorbed by the greenhouse gases on the way in that was not absorbed when we didn't have greenhouse gases. Let's think about what's going on the way out. Okay, on the way out, the Earth is going to emit lower energy infrared. The Earth is not the temperature of the sun, so the Earth is going to emit at a lower energy level for the IR. And what you're seeing here is that here's all the energy coming in from the sun, here's the IR that's being emitted, and all of the IR that's being emitted, but this IR is going to be trapped by greenhouse gases on the way out. Well, you said we were trapping on the way in. What's the difference with the way out? We're trapping a different frequency now. We're trapping a different wavelength. Let's go into it a little bit more. On the way out, outbound, the Earth is emitting everything in black here. Look, it's a longer wavelength than the visible wavelengths here. The Earth is emitting the longer infrared wavelengths that are lower energy. When it emits that, it runs into CO2 up in the atmosphere. Look, the CO2 absorbs quite a bit of the outbound energy. Look at the water vapor. It absorbs a lot more of the outbound energy. That's something we're really going to be talking about for climate change, because that absorption by the water vapor is the real issue here. We can't do much about water vapor. We can do a lot about carbon dioxide, and that impacts water vapor, and we'll talk about that more with climate change. Here's what I really want to make sure you understand. There is a vent. We have a vent here right between 8 and 12 micrometers. Right between 8 and 12 micrometers, there's not a whole lot absorbed from CO2 and from water vapor. There is some absorbed from ozone, O3. But to be very honest, with a healthy ozone layer, that absorption is not as great as that, because the ozone layer is so wrapped up in absorbing all the UV. So we do have a window to vent out heat between 8 nanometers, micrometers and 12 micrometers, and that is how the Earth vents out its emissions in IR through that window. So the Earth's emissions move out to space through that vent because radiation is what can move through space. Conducted energy can't move through a vacuum. Convected energy can't move through a vacuum. Only radiant energy can do that on the emissions. And so that's what we're looking at for this. That's what keeps our planet with an atmosphere with greenhouse gases in radiative equilibrium. Our atmosphere with greenhouse gases is not a black body because the atmosphere doesn't absorb everything. It absorbs selectively. The greenhouse effect is absolutely critical to our life on Earth. We couldn't be here without that warming effect. That has to do with absorbing incoming and absorbing emissions. Couldn't go anywhere without it. However, greenhouse enhancement is what we're discussing when we're discussing rising CO2 levels that impact rising water vapor levels, that really drive a lot more absorption of the outgoing emissions that really warm back when they reflect it back down to the Earth. That warming cycle leads to more ice melt. More ice melt leads to more evaporation off the oceans because there's more water around. That leads to more water vapor. That leads to more clouds. That leads to more IR absorption by the water vapor. That leads to more ice melt. That's what we call a positive feedback loop. What starts comes back around and gets reinforced, a positive feedback loop. The real issue here is going to be studying cloud formation. We don't have enough information on that. Remember, atmospheric science is a very young science. We're wondering, is it going to be a positive feedback loop where more ice melt leads to more ice melt? Is it going to lead to more IR absorption and warming? Or is it going to be a negative feedback loop? And what that means is that it could say more ice melt is to more evaporation, is to more water vapor, is to more clouds. Clouds do more reflecting. Reflecting does more cooling. I'd love you to pick up on some of that research. I'd love you to be an atmospheric scientist who figures that out. It's going to be key for us. Finally, Earth's energy equilibrium, what comes in equals what's going out. This is out of NASA and their CIRRUS satellites, and it looks complicated, and what it comes down to is this. Whatever comes in yellow either gets reflected out or absorbed, and all of the orange is moving out. The numbers add up. Let me show you. What we're talking about is 344 incoming solar radiation units. There you go, 340. And we balance that by reflecting out 99 units and emitting out 240 units. You can look at all of this here on the PDF, but all of this balances to keep the Earth in radiative equilibrium. If we keep adding CO2, we're going to have a net increase. We will eventually move off into another equilibrium, but the equilibrium will be warmer. All right, hope that helps you out. Take care, and we'll talk on the other side.